So let's talk about the interaction of light with our coordinated covalent complexes and try to make a link between the color of these complexes and the interaction of light with them. Alright, so one thing I need to remind you of is that when it comes down to the visible spectrum, we're actually talking about a very small portion of the visible spectrum, but this is the one that is in charge of substances having a particular color as far as we perceive it with our eyes. And specifically, we're going from a value of about 400 nanometers, which is in the violet purple region, up to about 750 nanometers, which is the red portion of the spectrum. Now, for the calculations that I'm going to show you in a second, instead of dealing with nanometers, which is inversely related to energy, or even energy in joules or kilojoules per mole, we're actually going to look at inverse centimeters, which is kind of a traditional unit when it comes down to spectroscopy. And the idea right here is that to go from nanometers to inverse centimeters, also known as wave numbers, technically what you have to do is convert nanometers to centimeters, right? So you'll have to do that conversion first, and then take the reciprocal of that answer in order to get inverse centimeters. Okay, so basically the smaller the number for the wavelength is, the larger the number for the wave number ends up being. So the violet has a higher energy value, 25,000 inverse centimeters versus 13,000 for the red portion of the spectrum. And another way to look at this is to think of it in terms of a unit circle, a color wheel specifically that depicts the different colors in the visible spectrum, right? We have the red, the orange, the yellow, the green, the blue, and the violet. And the wavelengths do decrease going counterclockwise on this circle, starting from the red, going all the way up to the violet region. And as I just mentioned right here, the shorter the wavelength, the higher the energy. This is a corollary of the Planck's constant and ultimately Planck's equation. All right, now in terms of correlating the light to the wavelengths that are being absorbed or transmitted, the way in which you can think of this, and it's a rather simplistic way of thinking, it doesn't always work, but for some complexes it actually does a fair job of assessing what the color of the complex is going to be. Technically, the idea is this: if you absorb a wavelength, and let's say that the wavelength we're absorbing is on the orange color, all right, so let's say it's 600 nanometers. Okay, so it absorbs in the orange. That means that that particular color does not get to be observed by us because the complex is taking it away from the light. And so what we're seeing is the complementary color, which is the color directly across from the orange. And that means that blue is the color that we will actually see. And so we will actually perceive the complex as being blue in color because it is absorbing the orange wavelengths of the light source that is interacting with. Alright, so that's kind of the idea. Absorb a specific wavelength of light, then the color of the complex, the actual color of the complex you're going to see is exactly the opposite in the color wheel. Alright, now another thing that's important specifically for your labs is the idea of concentration in regards to the Beer-Lambert law. So you may recall from Chem 201 or the first semester chemistry course that when you shine light through a solution that contains a solute in it, there's going to be some light that gets absorbed due to the interaction of light with the solute particles. So some of the solute particles absorb some of that light, and the decreasing intensity is what we associate to absorbance via the equation right here. More importantly, you can correlate the absorbance of a substance, of a solute, based on the concentration of that solute in solution. And the plot right here, absorbance versus concentration, is what we call the Beer-Lambert plot, which is a linear plot. The Beer-Lambert law has the simplistic equation: absorbance equals absorptivity coefficient times concentration times the path length. And unless otherwise stated, the path length, L, is usually 1 centimeter. But if ever mentioned to be anything else, make sure to input that value in the equation. Now the absorptivity constant here, if the concentration is molarity, this is known as the molar absorptivity constant. And as long as the path length is equal to 1 centimeter, the slope of this line is going to equal the molar absorptivity constant. If the concentration is anything else other than molarity, then this is just known as the absorptivity constant, still associated with the slope of this line. Now, for practical purposes, usually when you do absorbance versus concentration measurements and you try to get a Beer-Lambert plot, you want the concentration to be high enough that you are above 0.1 in absorbance, but low enough that you're below 1 for the absorbance. That's when you get the best precise results. If you get too high of a concentration, then you end up losing intensity of light, not due to absorption, but rather due to reflection or refraction, which is really not something you want to encounter, because now the decreasing intensity is no longer associated with the concentration of your complex, and that's when you introduce error. You may also recall using certain instruments. These are some of the typical UV instruments that you may use. And the instrument has a particular, this is not the only way to have a spectrometer, but this is one of the more traditional ones, where you have a tungsten deuterium lamp shining ultraviolet and visible light. That gets bounced onto a mirror, which then goes to a grating, which is the selector, the discriminator for wavelengths. This grating rotates, has a mechanical part that allows it to rotate, and basically selects the wavelengths that hit the second mirror. And depending upon how this rotates, you get a different angle of incidence for the different wavelengths. So you get only one specific wavelength to make it past this slit, which then goes onto the sample or a reference cuvette, and eventually the intensities of light reach the photomultiplier tube that gives you an analog conversion of your light absorption to electrical signal, which then you read out using a computer. Alright, so that's the idea in terms of how light interacts with your complex. And the big one, once again, has to do with the color wheel. So remember, light being absorbed is going to be the light that you don't see. The light that you do get to see in association with your complex is the one directly across in the color wheel. Alright, we're going to stop the video right now, and we'll start talking about the calculations involving the crystal field splitting diagrams in the next video.